I extend my warm welcome to all of you for this lecture. In this lecture, we are going to see the matrices, in particular, the eigenvalues, eigenvectors, and applications of eigenvalues and eigenvectors. First, let us see what is the definition of eigenvalues and eigenvectors. Let A be a square matrix. The characteristic equation of A is nothing but the determinant of A minus lambda I equal to 0. That is, determinant of A minus I, which is equal to 0, right? Now, the eigenvalues are nothing but the roots of the characteristic equation. For example, if A is the matrix ABC, D, E, F, G, H, L, and I is the identity matrix, that is 1, 0, 0, 1, 0, 0, 0, 1, and then A minus lambda I, which is equal to this one, right? This is A minus lambda, B, C, and then D, E minus lambda, F, G, H, and L minus lambda, right? So we have to find out what is the determinant of A minus lambda I equal to 0. That gives the characteristic polynomial, and then the roots of the characteristic polynomials are nothing but the eigenvalues. Okay, right. Geometrically, what it says, suppose if x is a vector, if you say that x is a eigenvector corresponding to the eigenvalue lambda, that means if you plug the vector x under the matrix A, that leaves some lambda times x. That means some scalar multiplication of the same vector x. Okay. Suppose if lambda is less than 1 by 2, then the length of the vector will be string. If it is greater than 1, then it will be elongated. If it is a complex number, then we will be having some rotation and a magnification. Okay, this is what the geometrical meaning of Ax equal to lambda x, right? There are some notes regarding to this characteristic equation. What it says, if A is n cross n matrix, then the degree of the characteristic polynomial is n. Okay, that is the nth degree polynomial, and then the polynomial will be of the form lambda power n minus s1 lambda to the power n minus 1 plus s2 lambda to the power n minus 2 minus s3 lambda power n minus 3 and so on, minus 1 raised to n, sn equal to 0. Okay. See, this is a general format. Hereafter we will be seeing when n equal to 3 or n equal to 2. Okay. Now what is S1? S1 is nothing but the sum of the eigenvalues of the matrix, that is nothing but sum of the main diagonal, or is nothing but the trace of the matrix A, right? Then what is S2? S2 is sum of the minus of the main diagonal of A. That means if you have the matrix 3 cross 3 matrix like this, 1, 2, 3, say for example 1, 2, 3, and then 0, 1, 2, then 1, 5, 6, then what are the minus of the main diagonal? This one is first minor. First find out the determinant of this, that is 1, 1, 2, 5, 6, plus, then for the diagonal element we have to have 1, 3, 1, 6, plus for this 6, 1, 2, 0, 1. Find out all these subdeterminants, then add it up, that gives the S2, right? And S3 is product of all the eigenvalues when n equal to 3, okay, when n equal to 3. In general, Sn equal to the product of all the eigenvalues, right? Now let us see first example. Find the characteristic equation of the 2 cross 2 matrix A equal to 1, 2, 0, 3, and hence find the eigenvalues of A. Now what is the general formula? General formula for the characteristic equation is lambda power n minus s1 lambda power n minus 1 plus s2 lambda power n minus 2 and so on. But the size of the matrix is 2 cross 2, so therefore we will be having second degree polynomial, that is, what is our polynomial? The general polynomial is lambda square minus s1 lambda power 1 plus s2 equal to 0. What is s1? S1 is nothing but the trace of the matrix, that is sum of the diagonal element, that is 2 plus 3. Okay, right. Then what is S2? S2 is the determinant of A, that is nothing but 6. See, therefore the characteristic equation is lambda square minus 5 lambda plus 6 equal to 0. And then the roots of this quadratic polynomials are 2 comma 3. Okay, this is a hint to find the roots of the characteristic polynomial. We have to use this formula, lambda equal to minus b plus minus under root b square minus 4ac upon 2a, right? Yes. Now let us see the second example. Find the characteristic equation of the matrix A equal to 1, 8, 5, 0, 2, 6, 0, 0, 3, and hence find the eigenvalues of A. Now the general formula is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. What is s1? S1 is nothing but the trace of the matrix, that is s1 equal to 1 plus 2 plus 3 equal 3, that is equal to 6, right? And then s2 is sum of the minus of the main diagonal, see therefore it leaves the value 11, and s3 is determinant of the matrix, so that gives the value 6. See therefore the characteristic equation is lambda cube minus 6 lambda square plus 11 lambda minus 6 equal to 0, right? Now it is a cubic polynomial. So we know how to find the roots of the quadratic polynomial. We have seen the formula lambda equal to minus b plus minus under root b square minus 4ac divided by 2a. Okay, but it is a cubic polynomial. See therefore we have to use some results. So what it says, the theory of numbers says sum of all the coefficients of the polynomial is equal to 0 means 1 is a root. Okay, and then the second note is sum of all the coefficients of odd degree which is equal to sum of the coefficients of even degree, then minus 1 is a root. Okay, now luckily if we add all the coefficients, what are they? 1 minus 6 plus 11 minus 6, but this is equal to 0. See therefore lambda equal to 1 is a root, right? Yeah. So from the note 1 we see that lambda equal to 1 is a root. To find the other two roots we use the synthetic division. Now let us place all the coefficients in this manner, that is 1 minus 6 11 and then minus 6. Already we know that lambda equal to 1 is a root, so therefore you start with 1, you start with the 0, then add these two, that is 1 here, then multiply this one and put it here. Okay, I am just multiplying this pink color one and then red color one get multiplied and then put it here, then add these two, that gives minus 5, and then multiply this one with the minus 5 and put it here. So if you add these two we are getting 6, and then multiply this 6 and 1 and put it here, that leaves 0. Okay, see therefore if you use this synthetic division method, that extract the quadratic polynomial like this. See therefore the cubic polynomial lambda cube minus 6 lambda square plus 11 lambda minus 6 equal to 0 can be written in the form lambda minus 1 into 1 lambda square minus 5 lambda plus 6 equal to 0. Okay, already we have extracted one first degree polynomial, that is lambda minus 1, and then to find the roots of this polynomial use the formula lambda equal to minus b plus minus under root b square minus 4ac upon 2a. Okay, that gives the values 2 comma 3. See therefore the roots of the characteristic polynomials are 1, 2, 3, right? Fine. Now let us move to the next problem. Find the characteristic equation of the matrix A minus 1 0 0 and then 1 5 0 minus 1 0 8, and hence find the eigenvalues of this. Now the general form of the characteristic polynomial is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. What is s1? S1 is nothing but sum of the diagonal elements, s2 is sum of the minus of the main diagonal, and s3 is determinant. Okay, right. So s1 equal to 12 and s2 equal to 27, right, and s3 equal to minus 40. See therefore the characteristic equation is lambda cube minus 12 lambda square plus 27 lambda plus 40 equal to 0. Now if you see that sum of all the coefficient which is not equal to 0. Look at this, what are the coefficients? 1 minus 12 and then plus 27, 27 and then plus 40, plus 40. See, therefore, which is not equal to 0. Therefore, lambda equal to 1 is not a root. Whereas, if we add the coefficients of odd degree, what are the coefficients? 1 and then 27. 1 and 27, and then the coefficients of even degree minus 12 and then plus 40. What is this? This gives 28 and then this gives 28. See, therefore, sum of the coefficients of odd degree which is equal to sum of the coefficients of even degree, hence lambda equal to minus 1 is a root. Again, by synthetic division we are extracting the another quadratic polynomial like this. Already lambda equal to minus 1 is a root, see, therefore you start with the minus 1 and then place all the coefficients like this, put 0, start with the 0 and then add these two, multiply this and this. So minus 1 into plus 1, that gives minus 1, and then add these two, it gives minus 13, and then multiply minus 1 with the minus 13, that gives 13, then add these two, it is 40, then minus 1 into 40, that gives minus 40, add these two, that leaves 0. See, therefore, the extracted quadratic polynomial is 1 lambda square minus 13 lambda plus 40 equal to 0, right. Now, if we solve this, we will get minus 1, 5 and 8 are the characteristic values, right. Now, there are some observations. The first observation is, if A is a diagonal matrix, that means only the main diagonal entries are non-zero, whereas off diagonal entries are 0. That is called the diagonal matrix. If A is a diagonal matrix, then the eigenvalues are nothing but simply the main diagonal element. That is, the diagonal elements are nothing but the eigenvalues, provided A is a diagonal matrix, right. Second observation, if A is upper triangular matrix, that means only upper triangular entries are non-zero, all the lower triangular entries are 0. That means below the main diagonal all the entries are 0. That is called upper triangular matrix. In this case, the diagonal elements are the eigenvalues of the matrix. Similarly, for the lower triangular matrix, the diagonal entries are the eigenvalues of the matrix. These are all some observation, useful observation we can use in some places, right. There is one famous theorem which is called Cayley-Hamilton theorem. What it says, every square matrix satisfies its characteristic equation. We know what is a characteristic equation of a square matrix, right. What is a characteristic equation of n cross n matrix? That is lambda power n minus s1 lambda power n minus 1 plus s2 lambda power n minus 2 minus s3 lambda power n minus 3 and so on, minus 1 raised to n, Sn equal to 0. Okay. Now, the above theorem says that in place of A, if you replace lambda by A, we will have the 0 matrix, that is A power n minus s1 A power n minus 1 plus s2 A power n minus 2 and so on, and then Sn into I, which is equal to, this is called a 0 matrix, 0 matrix, okay, right. This is what the Cayley-Hamilton theorem, very useful theorem, right. So, if you know this theorem, then by using this theorem we can calculate what is inverse of the matrix, provided the matrix is non-singular, and then any powers of the matrix can be calculated by using the Cayley-Hamilton theorem, right. Now, let us see one or two examples. Find the characteristic equation of the matrix A equal to 1, 2, 3 and 2 minus 1, 4, 3, 1 minus 1, and verify the Cayley-Hamilton theorem. Also find A power 4 and A power minus 1, that is A inverse, right. Now, first let us write, for this type of problem, first we have to write down the characteristic equation. The characteristic equation is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. What is s1? Sum of the diagonal elements, s2 is sum of the minus of the main diagonal, and s3 is determinant. Okay, already we have calculated what is s1 equal to minus 1 and s2 equal to minus 18, s3 equal to 40. See, therefore, the characteristic equation becomes lambda cube plus lambda square minus 18 lambda minus 40 equal to 0. Okay, right. Now, what is the question? The question is we have to verify the Cayley-Hamilton theorem, and hence we have to evaluate a power 4 and a inverse. See, therefore, the theorem says that wherever lambda is there, you just replace lambda by a. For this, we need what is a square, a cube, all the things. Okay. Now the matrix A is 1, 2, 3, and then 2, minus 1, 4, and 3, 1, minus 1. How to do the multiplication? And then row is getting multiplied with a column, right? That is, let us do one evaluation, then we'll assume that rest can be done. That is 1 into 1 plus 2 into 2 plus 3 into 3. So what it gives? This is 1 plus 4 plus 9. See, therefore 14. That is the first element, right? Similarly, for the second position, we have to multiply this row with the second column, that gives 3. For this element, we have to multiply this row with the third column, that gives this value. For the second row of the a square, take the second row and then first column, that gives this element. Then the second row, second column, this gives this element. Then second row, third column, this gives this element. For the third row, you take the third row of this, multiply with the first column, that gives this 2. Then take the third row and second column, that gives this element. Then third row, third column, this gives this element 14. Okay, this is the way we are multiplying two matrices, right? Similarly, if you do this calculation, then we are getting the A cube matrix. A cube matrix 44, 33, 46, 24, 13, 74, 52, 14, 8, right? So what is the characteristic equation? The characteristic equation is lambda cube plus lambda square minus 18 lambda minus 40 equal to 0, right? See, therefore, what is our equation? Lambda cube plus lambda square minus 18 lambda minus 40, right? So what I told, wherever a lambda is there, you replace lambda by a. See, therefore, a cube plus a square minus 18a minus 40 into I. Okay, we have to evaluate this matrix and then add these four matrices, that leaves 0. Already we have calculated what is a cube, place it here, and a square is this matrix, and 18a, 18 is here, and a is this, and I means identity matrix, minus 40 into I. If you add all these element wise, position wise, that gives 0 matrix. So what it says, this matrix satisfies its characteristic equation, right? By using this matrix equation, what is the matrix equation now? A cube plus a square minus 18a minus 40i equal to 0, right? Now from this equation, we can able to calculate what is A inverse and A power 4, all the things. Now next we are going to see such things. Since S3 is not equal to 0, that means determinant of A is not equal to 0, see, therefore A inverse exists, okay? Linear algebra theory says that if the determinant is not equal to 0, then it is called non-singular. If it is non-singular, then the inverse exists, right? Now we have the equation, what is a cube plus a square minus 18a minus 40 equal to 0. See, therefore, if we keep this 40i in the left hand side and then push the rest of the things to the right hand side, we will be having this equation, that is 40i equal to a cube plus a square minus 18a. If you multiply, post multiply by a inverse, we will be getting 40 a inverse plus a equal to a cube into a power minus 1 plus a square into a inverse minus 18a into a inverse, right? But what is a cube into a power minus 1? By using the power law, then a to the power 3 minus 1, that is equal to a square, right? Similarly, a square into a power minus 1, that is equal to a, okay, and a into a inverse, that is equal to identity. See, therefore, we are getting this expression, a square plus a minus 18i, right? So I want what is a inverse, therefore multiply this equation by 40, that gives 1 by 40 into a square plus a minus 18i. Already we have calculated what is a square, a and 18i, plug all these matrices here, that gives the nice matrix A inverse equal to minus 13 upon 40 1 by 8, 11 by 40, 14 by 40, minus 1 by 4, 1 by 20, 1 by 8, 1 by 8, minus 1 by 8. Okay, it is easy to calculate. It is easy to calculate A inverse any powers of matrix by using the Kelly-Hamilton theorem. This is the application of Kelly-Hamilton theorem. Okay, so inverse exists provided the matrix is non-singular. If it is singular matrix, then we cannot be able to find out what is A inverse. In fact, A inverse does not exist for singular matrix. What is the next thing we have to calculate? We have to calculate what is A power 4. Okay, so A power 4, which we can write A cube into A square, right? So we know what is A cube. We know what is A cube, A square, A, all the things, and then by using the Kelly-Hamilton theorem, we have A cube plus A square minus 18A minus 40I equal to 0. See, therefore, from this expression, our A cube, which is equal to minus A square plus 18A plus 40I, right? I want A power 4. See, therefore, you multiply A cube by A. See, therefore, A power 4, which is equal to A cube into A, and then if you multiply A with this A square, that gives A cube, right? And then multiply A with A, that gives A square, multiply I with A, that gives A, right? Again A cube, which is equal to this expression, minus A square plus 18A plus 40I, replace this A cube by this expression. See, therefore, minus of minus A square plus 18A plus 40I, then the remaining things, remaining expressions, plus 18A square plus 40A, that is equal to 19A square plus 22A minus 40I, and replace the matrix A square by this, and then A by this expression, and I by identity matrix, then you have this matrix A power 4. Okay, no need to calculate A 4 times. It is very tedious job. Finding powers of the matrix, it is very tedious job, whereas if you apply the Kelly-Hamilton theorem, it is easy to calculate any powers of A, right? Very good. Then next, see the next example. Use the Kelly-Hamilton theorem to find the matrix equation. What is the matrix equation? A power 5. Look at this expression. It is a very complicated expression. So A power, this is A power 5 minus 4A power 4 minus 7A cube plus 11A square minus A minus 10I, where A is a 2 cross 2 matrix. Even if it is a 2 cross 2 matrix, then finding such a polynomial is very difficult. Why? Because it is a matrix equation. Okay, for this, first we have to find out what is a characteristic equation. For 2 cross 2 matrix, the characteristic equation is lambda square minus S1 lambda plus S2 equal to 0, where S1 is sum of the diagonal, that is 4, and S2 is the determinant of A, that is S2 equal to minus 5. See, therefore, this characteristic equation is lambda square minus 4 lambda minus 5 equal to 0. Okay, now we have to evaluate what is a matrix associated with this matrix equation. For this, the simple technique is divide the given matrix polynomial by the characteristic polynomial that gives a remainder as well as the quotient. See, therefore, any polynomial can be written in this form. Suppose P of x is a polynomial and Q of x is a divisor, then your P of x can be written as P of x into, P of x equal to the quotient polynomial into the factor, let me call this as h of x, plus the remainder polynomial x. Okay, here h of x is a quotient and q of x is the divisor, r of x is your remainder. See, therefore, by using this algebra, we can write the given polynomial as divisor into quotient plus remainder. Okay, so what is our characteristic polynomial? The characteristic polynomial is lambda square minus 4 lambda minus 5 equal to 0, and replace lambda by a. See, therefore, you will have a square minus 4a minus 5i, and then the given polynomial is a power 5 minus 4a power 4 minus 7a cube plus 11a square minus a minus 10i. Okay, look at this. The first term is here a square, but I want a power 5. I want a power 5. See, therefore, if you multiply this a square with the a cube, then I will get a power 5. See, therefore, the first term in the quotient polynomial is a cube. Multiply this a cube with this factor, you will get a power 5 minus 4a power 4 minus 5 a cube, and then subtract this, then this gets cancelled, remaining is minus 2 a cube. Now look at this constant term. The constant term is minus 2 into a cube, but we have 1 into a square. See, therefore, the opt term is minus 2a. If you take the second term as minus 2a, if I multiply with this a square, then I will get minus 2a cube. See, therefore, the second term is minus 2a, multiply with this factor and put it here. See, therefore, minus 2a cube plus 8a square plus 10a. Then subtract. This gets cancelled. What is the remaining? The remaining is 11 minus 8, that is 3. And then here a minus 10a, see, therefore 11a, and then 10i. Now look at this. Now this term is 3a square. I want 3a square, but we have a square here. See, therefore the next term will be 3. Now multiply this 3 with this factor and put it here. See, therefore the first term is 3a square minus 12a, then minus 15i. Then subtract it, then this gets cancelled. What is the next term? The next term is minus 11 plus 12, see, therefore a, and then here minus 10 minus 15i plus 15i, see, therefore this is a plus 5. Okay, a plus 5. There is a mistake here. This is a plus 5i. Okay, a plus 5i. Right. So this polynomial can be written in this form. What is this? A power 5 minus 4a power 4 minus 7a cube plus 11a square minus a minus 10i. So this is a characteristic polynomial, and this is your quotient, and this is your remainder. Okay. Now, as we know that lambda square minus 4 lambda minus 5 equal to 0. By Cayley-Hamilton theorem, we have a square minus 4a minus 5i equal to 0. See, therefore this expression is 0, right? See, therefore we are getting 0. The 0 matrix multiplied with this expression and this remaining factor. Any matrix multiplied with the 0 matrix, that gives 0 matrix. See, therefore the remainder is a plus 5i. What it says, this bigger expression reduces to a linear polynomial like this, a plus 5i. Already we know what is a is 1, 4, 2, 3, and then 5i is the scalar matrix 5, 0, 0, 5. If you add these two, we will get the simple matrix like this. Right. So this is another application of Cayley-Hamilton theorem. Okay. These are all some exercise. Please do it. Next we will see the eigenvectors. What is the definition of eigenvector? A non-zero solution of the system of equation, a minus lambda I into x equal to 0. Okay, that x is called the eigenvector. Okay, what is the first observation? A non-zero solution of the homogeneous system a minus lambda I into x equal to 0. Okay, very well. If you take x equal to 0, then the system will satisfy, right? But we don't want zero solution. We look for the non-zero solution. So hereafter the eigenvector means it must be a non-zero vector. It must be a non-zero vector, right? Yeah, let us see one or two examples how to find the eigenvalues and then eigenvectors for simple matrices. Then we will see how to find the diagonal matrix by using the eigenvectors. Right. Let us take the first example. Find the eigenvectors of the matrix 2, 1, 0, 3. Now the characteristic equation already we have derived, lambda square minus 5 lambda plus 6 equal to 0, and then the roots of the characteristic polynomials are nothing but lambda 1 equal to 2 and lambda 2 equal to 3, right. So what we are looking for? We are looking for what is x for the 2 cross 2 matrix, therefore let it be x1 comma x2. So let us assume that the eigenvector is x equal to x1 comma x2 be a vector such that a minus lambda I equal to 0. Okay. Now we have two values for lambda, lambda 1 equal to 2 and lambda 2 equal to 3. For each lambda we have to find out one vector, right. Now let us take the first eigenvalue lambda 1 equal to 2 and then replace lambda by lambda 1. See, therefore we will get the matrix equation a minus lambda 1 and I, okay, that is 2 minus if you replace lambda 1 by 2, that is 2I. See, therefore 2 minus 2 1. What is actually a? A is 2 1 and then 0 3, right. Then minus what is 2I? 2I means 2 0 0 0 2. Okay. If you subtract this, what you will get? This is 2 minus 2, 1 minus 0 and then 0 minus 0 and 3 minus 2. See, therefore that gives the matrix. What is this matrix? 0 1 0 and then minus 1. Okay. So this gives